Okay, so logarithms. You may have seen these superficially before in chemistry, for example, because pH, the pH scale, which measures the level of acidity in a solution, is an application of logarithms, okay? But you probably haven't seen much about what they mean yet, okay? So we're going to talk about that a little bit today, and we're going to talk about logarithms over the next couple of classes. So a logarithm is another form of a power, okay? Whoops, there we go. And in this form, we are actually able to isolate the exponent. Thank you. Okay, so let's say, for example, I know that, I don't know, 3 to the 4 equals 81. Okay, so this is a power, it has a base, it has an exponent, and it's equal to a value. In logarithmic form, we would say a logarithm, the logarithm with a base of 3 of the value 81 is equal to 4. Okay, so all of the numbers that we see in a power, including the base, the exponent, and the value, sort of go to different places in logarithmic form. And essentially, when you see this, and you want to say, what does that equal? What you want to ask yourself is 3 raised to what exponent gives a value of 81? Right? So essentially, this means 3 raised to what exponent? Whoops. Has a value of 81. Right? So you're kind of solving 3 to the what equals 81. And we know 3 to the power 4 equals 81. And so the value of this logarithm is 4. And in exponential form, that would be the exponent part. Okay. Now, why do we do this? Well, there are certain applications in the world where it's more simple to just keep track of the exponent on a value rather than the value itself. And that is typically when we're looking at measuring something that has an enormous range of values, right? Because then instead of having to write out numbers that are incredibly, incredibly large, right? We're talking about, I don't know, 20-digit numbers, 30-digit numbers, that sort of thing. Or, on the other hand, incredibly, incredibly small, like 0.15 zeros and then another number. Instead of having to do that, we can just keep track of the exponent of that number, usually with a base of 10, or there's another common base that we often use, and then we measure that instead. Okay? And then it's just like we're dealing with smaller numbers. And so one example is concentration of acid in a solution. Turns out that there's an incredibly enormous range of values that you can have for the concentration of acid in a solution. So instead of having to write those down, and in that case, they're usually very small, we just keep track of the exponent on a base of 10 of that concentration, and then we can kind of use whole numbers or not exactly whole numbers, but pH is like anywhere from 0 to 14, and neutral is 7, and if you go, the lower it goes, the more acidic it is, and the higher it goes, the more basic it is. Is that right? Or am I getting it reversed? Okay, cool. It's been a while. And so we can just keep track of that exponent instead of having to keep track of the actual concentration. Because when we have to keep track of the concentration, it's very easy to accidentally drop a 0. You don't want to do that because that could have massive effects on whatever you're doing with that acid, right? Another example of this is looking at the intensity of an earthquake, okay? So instead of actually writing down the intensity, like something in the millions or billions or whatever, or even just thousands, we keep track of just the exponent on that intensity, and that's called the Richter scale, okay? So we are going to get into a lot of applications later down the road, but I want to kind of explain why we do this in the first place, because sometimes it's like, what's the point of this? Where are we going with this? Okay? A common logarithm is a logarithm that uses base 10. Now, when you are dealing with a common logarithm, you don't actually have to write that little number down there. If you don't see that number, you assume it's base 10. Okay, so log base 10 of whatever number is just equal to log x. You don't explicitly have to write that number 10 in. If you don't see it, it's base 10. Okay? It's kind of like when you're taking a square root. You don't have to write the little 2 inside. If there's no number there, we assume it's a square root. Right? If it's any other root, a cube root, a fourth root, whatever, we have to write that little number in the index. Okay? Same sort of idea. Okay? So for example, if I'm looking at the log of 1,000, okay, essentially what I want to know is we have to remember that there's an imaginary 10 in here. It's not usually written in. It's considered like redundant to write that in. If you want to write it in yourself because it helps you to remember, that's totally fine, but you won't see it written that way. What we are asking is 10 raised to what exponent equals 1,000? 10 to the power what equals 1,000? Yeah, 3. So the answer to this, or the value of this, is 3. Okay? Now, one thing that you could be asked to do, and this is a very simple, hopefully, task, is just to switch forms, right? Can you go from exponential form to logarithmic form? Okay? And I believe, actually, this is on your formula sheet. Yes, it is. So essentially, if we look at exponential form, okay, we have a to the power x equals y. Okay. In logarithmic form, okay, the base of the exponent becomes the base of the logarithm. So here we are going to have log with a base of a. Okay. The value of the power goes over here. So the value of a to the x is y. This goes here. And the log is the exponent. So that's equal to x. Okay, and this is on your formula sheet. And a lot of people often kind of get confused about what goes where, particularly mixing up x and y. Usually people remember the base becomes the base. So please have that out as a reference and just kind of plunk things in the right space. Okay? So we're going to practice this a bit. Okay? Express the logarithmic equation as an equivalent exponential equation. Okay, so now we're going from the log form to the exponent form. Okay, so what is the base of this exponent? Of this power? Yeah, it's 2, right? Because it's the same as the base of the logarithm. Okay, what is the exponent on 2? Exactly, y, and that is equal to 8. Okay, now is this something that you could evaluate? Could you tell me what y is? Yeah, what's y in this case? It's 3, right? Because 2 cubed equals 8. So some of these we can evaluate sort of algebraically. Some of them we can't. We'll talk about that as we move through this unit as well. Okay? So let's now go the other way. We've got 12 to the 2x equals 4. Okay? All right, so we're going to put this in log form. Sometimes I encourage people to do this. Log of blank equals blank. And then just fill in the blanks. Okay, so what's the base? What should go there? 12. And what's the value? What should go here? 4 equals 2x. Yeah. Okay, so you guys give these 2 a try. Or these 4, rather. No, these 8. There's 2 questions here. There's 8 for each. Okay, and then we will keep going, hopefully. Okay, so the next thing I want to talk about is how to evaluate logarithms. And we've already sort of touched on these. Now, some people were asking me, how do I plug like log base 3 of, I don't know, 25 into my calculator? And the answer is that you can't. Because if you pull out your calculator, you look on the left-hand side, you have a log button. Okay? But that log button doesn't have, remember what the base is when there's no number written in? It's base 10. So the memory of your calculator actually only stores logarithms of base 10. Okay? And by the way, where's my, here I have a log book here. Okay, so this is what was used back in the day. This includes tables of logarithms and tables of trig ratios for every single angle. Okay, this is my aunt's. She graduated from high school in like 1962-ish, something like that. Okay, and up until, I don't know, 30 years ago, people had to use these because calculators were kind of, you know, not as advanced as they are today. You couldn't store as much information in them. And so the logarithms with a base of 10 were all stored in these. And now they're just stored in the memory of your calculator. So I always joke when people forget their calculators and we're doing something with log and trig, I'm like, forget your calculator, you can use one of these. But actually, I wouldn't do that to you, okay? But if you see along here, you've got this button log, and it just opens up a bracket, and you could put any number in there. But you can only calculate logarithms on your calculator that are base 10, right? So let's say I wanted to know the log of 50. This essentially is asking 10 to the power what equals 50? Well, there's not going to be an exact value there because 10 to the 1 equals 10. 10 squared equals 100. 50 is between 10 and 100, so the exponent should be between 1 and 2, right? And that's what we see. It's between 1 and 2, right? So these are the only values that are stored in your calculator. There is also another base that's stored in your calculator, and that is this button, ln. We don't really get into this much in this course, except when we do regression. And the base of this logarithm is a number called e. And e is equal to about 2.7. But it's like pi. It's just a number that keeps going on and on and on and on. And we don't really get into this one too much in this course. But that's the only other base that's stored on your calculator. Every single other one is not in the memory of your calculator. Okay? We'll talk about how to work with that. A lot of times you can solve these algebraically, right? So we're going to talk about that first. If you can't solve them algebraically, like for example, log base 10 of 50, can't do that algebraically because 50 is not a power of 10. We'll talk about some workarounds probably tomorrow or next week. Okay? But we can solve a logarithmic expression by essentially setting the logarithm equal to a variable. So that's what we're going to do first. Okay. And then once we have that logarithm equal to something, we can switch to exponential form and solve the exponential equation, which we just spent some time doing this week, right? So for example, if I wanted to know log base 5 of 625, and I wanted to know what's the value of that, what I can do is set this equal to a variable. Once I have that variable in there, there's now like 3 sort of numbers or variables, so I can plunk that into the exponential form, right? So in exponential form, my base is 5, my exponent is x, my value is 625. And the hope is that this is something that I can solve. If I can write 625 as a power of 5, then I can solve this, right? And in fact, I can. 625 is actually equal to 5 to the 4. Once the bases are the same, I can conclude that the exponents are the same. So x here has to equal 4. And x is also what I set equal to that logarithm. So if x equals the logarithm and x equals 4, I can conclude that the logarithm equals 4. And that's the value of the logarithm. Okay? So let's practice this. Evaluate the following logarithms algebraically. So what we're going to do is set this equal to a variable. Actually, this one's really similar to the one that we just did. And then switch forms. Okay? So my base is 5, my exponent is x, the value is 15,000 rather, 625. And now this is an exponential equation. And with exponential equations, we try and change the base, one of them or both of them sometimes, so that they are the same. So can I write 15,625 using base 5? I can. Okay, so what is the exponent then? Is it 5 to the 5 or 5 to the 6? Okay, this is 5 to the 6. So I can say 5 to the x equals 5 to the 6, and therefore x equals 6. Okay? Start this one the same way. Set this guy equal to a variable. Okay, and then I'm going to switch forms. So my base is 2. My exponent is x. My value is 1 over 32. Okay, so this is another one of those questions where that power of 2 is actually in the denominator. So when you see something like that, don't worry about the fact that it's in a fraction yet. Just see if you can express 32 rather, the denominator, using a power of 2. Can we do that? Yes. 2 to the 5. So I'm going to keep going with that. Oh, whoops. 2 to the x, rather, equals 1 over 2 to the 5. Okay? Now, this is not base 2 yet because it's in the denominator. How could I bring this up? What would happen?
Make it a negative.
Yeah. If I bring this up, the exponent becomes negative. And then I can conclude that x equals negative 5. Okay? All right. So here we have a question where both the base and that value are written with variables. But let's just sort of apply the same thinking. If I set this equal to x, then my base is b, my exponent's x, and that equals 1 over b to the 4. Okay. Are my bases the same yet? No. How do I make the bases the same? Yeah, bring it up and make it negative, right? So b to the x equals b to the negative 4. So x equals negative 4. Okay? This next one. So if I set this equal to a variable, I keep using x, but you can use whatever you want. What's the base of this logarithm? 10. Exponent is x equals 25. Okay. So is there a base that will work here? No. Right? 25 rather cannot be written using a base of 10. So this we can't solve algebraically. I should say can't solve it algebraically yet. By mid next week, we'll be able to solve this algebraically. But common logarithms are stored in the memory of your calculator. Okay, so if you do see something that's a common logarithm, just log of a number, we assume the base is 10, you can get the decimal approximation by just evaluating on a calc. Right? Again, only works for common logarithms. So if I take out my calculator and I put in the log of 25. By the way, look at this equation before we do that. What two whole numbers will x be in between? 1 and 2. Yeah, because 25 is between 10 to the 1, which is 10, and 10 squared, which is 100. So we would expect that this will be somewhere between, it's going to be 1 point something. There you go. 1.4, roughly. Okay. All right. So I would like you guys to evaluate these, and we're going to leave it there for today.